So let me begin by recapping some previous results. We are considering a scenario where a theory is described by certain basic ingredients which are the endpoint Green's function, denoted as Gn with n points in the argument. And we have seen that this can be given by word-line diagrammatics, word-line theory diagrammatics. So this is given by word-line theory diagrammatics. And these diagrammatics, what go into this is the word-line theory path integral, and certain topological aspects. Some topological inputs that go in to find this, to express these Green's functions. And what we are doing now, this is what we have done earlier. What we are doing now is we are considering a claim that in space-time QFT, the same Green's function is given by the vacuum expectation value of the time ordered product of the n factors of this scalar field. And so this is the interacting theory vacuum, and this has a path integral expression, which is a generalization of what we have proved in non-relativistic quantum mechanics. So you remember that for the 2-point function, the same quantity when n equal to 2 has been shown to be equal to a path integral for the word-line theory. And we discussed that the equality of these two quantities is not proved. We find them to have the same results. So for every path integral expression, there is a corresponding canonical expression in the canonical theory, like Schrodinger theory. Or we did not develop the canonical theory for the word-line description. Nonetheless, the word-line path integral was shown to be the 2-point function here. Now what we are doing is we are starting with the canonical expression in the context of QFT, and using the same results of non-relativistic quantum mechanics, which we proved that a canonical matrix element calculated in the usual Schrodinger theory with certain insertions is given by the path integral for certain type of theories where the Hamiltonian has the standard form. And our quantum field theory also, the Hamiltonian has the same standard form, and therefore we can use that result as a theorem and use the same mathematics here. And it is just that. So doing that, we get the path integral expression for this quantity, which is given by integral d phi exponential I over h bar is phi x1 to phi xn divided by integral d phi exponential I over h bar is phi. And both these two denominator and numerator, both of them are boundary condition dependent. But the ratio is not. And we developed certain other tools, which we call generating functional, in terms of which also the GN can be described, and this generating functional and the relation between GN and generating functional is the following. So this W is the generating function. And it is given by the following expression: d phi exponential I over h bar is phi comma j divided by integral d phi exponential I over h bar is phi. And this s phi comma j is nothing but s phi plus h bar j phi, where we use this notation, this bracket notation is integral d dx jx phi x. Okay. Then yeah, for completeness, let me also write down the theory for which this is valid. This expression, path integral description of this quantity in terms of path integrals, where we use the non-relativistic quantum mechanics result. The theory should be of this form. So action is given by this. And so on. Okay, now our Minkowski space metric signature is mostly positive, and this omega and phi equal to 0 configuration are in one-to-one correspondence. So phi equal to 0 in field theory corresponds to the vacuum, interacting theory vacuum in canonical quantization. This is what we have already done. This is what we are doing now. So the goal now is to understand the computation in this QFT side and show that we get the same Green's function, same diagrammatics that we discussed earlier using wordline arguments. So let us first demonstrate this with the free theory. So demonstrate with free theory. Free theory we will be denoted with a subscript 0. So what we do is to Fourier transform. Fourier transform both phi and j using this formula. Then calculate action. I mean S0 S phi comma j in terms of phi tilde and j tilde. So calculate action in terms of phi tilde and j tilde. Show that this is straightforward. Which is given by minus half del mu phi plus m square phi square plus h bar j phi. Show that this, when you write it in terms of Fourier transformed fields, one gets this result. One should use, so this, if this is the Fourier transform, then usually in these calculations you have to use the expression for the Dirac delta function, which is given by d dx over 2 pi to the power d to the I p plus q dot x is equal to the d-dimensional Dirac delta function. Then so here we say this is a mistake here. This is j tilde phi tilde. So because of this j phi term, it is not a perfect square. So you can complete the square, because there is a you have an x square, an a times x term. So what you do is write it as a plus x plus a whole square minus something. So that's a standard procedure called completing the square. And in order to do that, you have to do a substitution. Here in this case, the substitution reads as phi tilde p is equal to phi tilde prime p plus h bar times p square plus m square to the power minus 1 j tilde p. With this substitution, show that S0 phi comma j is given by integral ddp minus half p square plus m square phi tilde prime p phi tilde prime minus p plus h bar square by 2 p square plus m square inverse j tilde p j tilde minus p. So of course this first term, so you see there is no cross term here. So the first term is entirely dependent on phi prime, and the second one is dependent on j tilde. Now this first term, you see this S0 has this term. If you set j equal to 0, then that is S0 of phi. This term is just S0 of phi, the actual action. We had added the source term. So the actual action is this. So this is nothing, and this first part is nothing but the actual action calculated at phi prime. So this is A0 of phi prime. So now go ahead and calculate W0. So W0J is equal to integral d phi exponential I by h bar is 0 of phi prime plus I by 2 integral ddp h bar j tilde p j tilde minus p over p square plus m square. This had one h bar square, but then we had I over h bar outside. So one factor of h bar gets cancelled. So you have only linear in h bar term, and in the denominator you have the same thing, exponential I by h bar is 0 phi. Now you see the first term here, this exponential is 0 phi prime. Now phi prime and phi are related by a constant shift for the, as far as the phi path integral is concerned, because this is independent of phi. This is like a constant shift. So d phi prime is same as d phi is same as d phi prime. So because d phi prime is same as d phi, these two factors will cancel, because phi prime, you can think of this as d phi prime, and therefore d phi prime e to the power I by h bar is 0 phi prime is same as d phi to the power I by h bar is 0 of phi or phi prime being a dummy variable. So these two factors will cancel, and therefore j0 of j will simply be this this one, which is independent of any so this is like a exponential of, sorry, so exponential of this factor is a constant factor as far as this path integral is concerned. So this can come out, and the rest will cancel between upstairs and downstairs. So this means that W0 of j is given by exponential I by 2 integral dtp h bar j tilde p j tilde minus p over p square plus m square. And then you can simply apply the inverse Fourier transformation. And okay, so let me write that expression in the next slide. So this is the first part.